And we're live. All right, it is Thursday, January 8th, 2015, first TV Hangouts of the year. It's 11 o'clock Pacific, and today we're going to be talking about more compression. If we have time, so compression, we'll probably have time after we talk about it, but then we're also going to move on to InnoDB I/O capacity. It's a fun variable, and just kind of get everyone's understanding of what it is and what it does. And if we have time, the MySQL event scheduler. So without further ado, let's kind of get started. Quick round of introductions. I'm Jeff. I am a DBA at Box. Go ahead, Daniel.
I'm Daniel. I'm a DBA at Snow.
Okay. Jeremy.
Jeremy Tinley, database guy at Etsy.
And John.
John Cesario, DBA at Square.
Matt.
I'm Matt Lord, and I'm a product manager at Oracle.
Morgan.
Morgan Tucker, community manager at Oracle.
And Tim.
I'm Tim Callahan from Tokutech, and I am really cold.
I was wondering why you had a sweatshirt today.
It's 0 degrees out right now in Massachusetts.
0 Fahrenheit or 0 Celsius?
Fahrenheit.
Fahrenheit.
Okay, so it's actually really cold.
It's minus 30 here, and I don't have to say Celsius or Fahrenheit because it matches.
All right, so yeah, why don't we go ahead and get started talking about compression. So last time we spent a pretty good amount of time talking about it. And so Tim was gracious enough to put together some slides to talk about compression in TokuDB because that was one of the questions that we had come up. And hopefully Matt and Morgan, between the two of you, can give us a little more history on InnoDB compression until we can get someone who definitely has more involvement with it. But just having general conversation about it, I think, would be fun. So without further ado, you want to take it away, Tim, with what you've got?
Yeah, let me bring up my screen share.
Okay.
And hopefully nothing pops up on Skype that I don't want you guys to see.
Oh, well, let me put the camera on me. All right, good.
Okay. Can you see that now?
Yep, looks good.
Okay. So, hopefully what we have here is just educational, arguing the relative merits of one way to do compression over another is probably a fool's errand and not worth spending much time on. But I'm happy to go as deep into the technology of how we do compression as possible. On the last slide, I talk a little bit about spinning disks versus SSDs because it's not a one-size-fits-all solution. You do have to do some tuning. But please, along the way, you guys just jump in with questions if you have them. So, just very high level, if we take a peek, this is a fractal tree index is a B+ tree from an implementation perspective. It's a little bit important that we understand this. So we have a root node at the very top. All non-leaf nodes we call internal nodes. So a root node is special in that it's the top of the tree, but it's really no different to us than an internal node. The nodes up above carry messages in our implementation. Leaf nodes are where the actual row data itself gets stored. Really, a really important decision that we made early on, and this was pre-compression. Compression wasn't in the initial implementations of the fractal tree. So similar to InnoDB, we added compression after the fact. Wasn't an original design tenet of the system itself. But a huge difference here is, as the header says, fractal tree nodes are very large, and that largeness is going to add to some nice compression benefits. But by large, if we drew these things to scale, InnoDB the nodes be tiny compared to TokuDB. So by default, a node in TokuDB and root nodes, internal nodes, leaf nodes, they're all the same size on a tree. Default size is 4 megabytes. It's configurable. You can set it to anything you want. In comparison, InnoDB defaults to 16. I think there's probably use cases, maybe on really fast flash storage, where you might want to make that 8 or 4 for point queries and performance. And I do follow a lot of what the InnoDB team writes about. They blogged, I think, in 5.7. They're adding the ability for InnoDB pages or nodes to be 32K and 64K. And it looks like the initial implementation of that's going to be won't support compression at those higher page sizes. But I think there's code in that direction. And when they get there, you're going to see there's significant benefit. When you start with something larger and you compress it, you tend to end up with a better compression ratio than you do with something small. I've done lots of experimentation. It feels like the sweet spot on compression is generally around 48 kilobytes. After which 64, 128, 256, you do get small increases in compression benefit, but nothing near what you find when you go from 16 to 32K or 32K to 64. So our default node size is 4 megabytes. It's enormous. One of the reasons we started out with that number was the fractal tree originally was built in a time of spinning disks. And the original goal, why it's 4 megabytes, is we decided that the time, we wanted to make sure we consumed as much disk bandwidth as the seek took. So we figured if it took 4 or 5 milliseconds to get to a point on the disk, we also wanted to peel back between 4 and 5 milliseconds worth of transfer, which works out to something near 4 megabytes on technology, circa 2008, 2009. Completely configurable. I still leave, for all my benchmarking, the node size at the 4 megabyte default. So if we crack open a leaf node at the very bottom of a fractal tree, this is again where all your row data is going to be stored. And we stack it up and rip it apart. If you look at that stack to the left, that represents about 4 megabytes of data. Keep in mind it could be larger. So TokuDB, our max row size in TokuDB is 32 megabytes. InnoDB I think has some ridiculously larger number, like measured in gigabytes I think, for really big data. But our max row size is capped at 32 megs, can't be larger. So the reason I say less than or equal to 4 megabyte is we certainly support bigger row sizes. If you were to put a 32 meg row in a table, then I can't hold that in a single 4 megabyte leaf node. So the leaf node grows to accommodate the row. We don't store the row over a series of leaf nodes, but it would be a really bad idea to have a 4 meg leaf node in a 32 meg row. You'd probably want to make your leaf nodes bigger, or I'd probably recommend that this use case store their data somewhere else with row sizes that large. So we start with that 4 meg row, and we chop it up. If you look at that box on the right, just some other, I think, interesting things to note. They don't have much to do with compression. A neat little comparison with InnoDB. So we store the entire row inline in the tree. InnoDB, I believe, has some kind of number at which it decides it's going to store X% of the row inline, and the rest of the row goes somewhere else. It's probably using that for blobs and such. Because you're probably not accessing the blob data nearly as much as you are the rest of the data. The other thing we do differently is our MVCC data for MVCC queries, for example. That goes inline as well. So everything we're doing is inline. If you have multiple versions of a row that haven't been garbage collected because of outstanding transactions, that MVCC data is going to be right in the leaf node as well. It's not going to actually be in some other data structure, some other part of the cache table, some other part of the file system. And in memory, these leaf nodes are always uncompressed in the cache table. So, but looking at the left here, if we cracked open a leaf node, and this is definitely not drawn to scale, but I needed the room at the top. So every leaf node at the very top of it has a header. I think it's less than a kilobyte. I'm not sure exactly what the number is, but it's tiny. So remember, this isn't drawn to scale. One little piece of the header, I think it's just a single byte, we use to represent the compression type. So TokuDB supports uncompressed data if you really don't want to compress at all. But then QuickLZ, zlib, and LZMA compression are currently supported, and we're adding support for Snappy in the next release near the end of this month. So we take the first byte of the header, or give or take, and we store a single byte integer there to let the system know that when I go to read the rest of this off of disk, and I need to decompress it, I need to figure out what compressor was used to compress it in the first place. So we take a byte, and that allows for up to 255 or 56 compression algorithms. We're nowhere near that, but it's important we know how the block was, how the node was compressed. The rest of the header is nothing more than these, as you can see here, this min key, max key, and then offset. And the point of it is this: we want to make sure when you come down into this leaf node that we can subdivide what remains in the leaf node for efficiency. Because these nodes are so big, we can put a lot of row data there, and if we wanted to do binary searches on this row data, it would be a lot less efficient than being able to jump in smarter. So the example I drew here was this 1-5:4096. What I'm saying there is that it's key value at the bottom of the stack here. So keys 1 through 5 are available in this leaf node at offset 4096 in memory. Then I've got keys 5 through 10 at 62, 128, ... the very bottom basement node there, I'm saying keys X through Y, it would be kind of the highest value keys, are available at offset Z. So cracking this thing open, then when you look at the basement nodes below it, that first, if I were looking for key 4, I would note that it's between 1 and 5. I'd jump into this basement node. It's about 64K by default, the basement node. And then the row data is stored in sorted order. So I can do a quick binary search within it to get to that data. I'll talk a little bit about basement nodes on the next page, but essentially this leaf node itself, if you were to crack it open, I've seen some presentations at Percona Live where they kind of really get into the details about how InnoDB stores data and kind of cracking it open. This, I think, might pique people's interest a little bit in terms of how the data is actually getting stored itself. But think of it as this: leaf node, 4 megabytes of data, a very small header at the top telling us compression and letting us efficiently within that leaf node get to the data we want. It's zoned in these little basements. Within the basement, the data is stored in ascending key order.
I have a quick question here, Tim.
Mm-hmm.
So with the ranges and the offsets in the header, so are those calculated based on just looking at the basement node stuff that you have? So do you try to pack about 64 kilobytes of raw record data, and then that influences the record and offsets that go into the header, or do you always do it like we're going to put 5 records here, 5 records there, and so forth?
What we try to do, again, I think this is more of an after the fact. One neat property of calling this a fractal tree, fractals, when you zoom in, they kind of look the way they did before you zoomed in. You zoom in again, it looks the same. What's actually going on in this leaf node, it is kind of a mini tree in itself. So these basement nodes, there's an actual data structure behind what you're seeing here, which is a tree. And when we first create a leaf node, we create one basement node, and it's 64K. And when we get almost full, or when we hit 64K, we split it into 2 32K basement nodes, and it gets its own little, it's split apart. And then when one of those guys gets too large, it'll split into 2. When, if you're deleting data and it gets smaller, it'll collapse and merge adjacent basement nodes back together. So its target is like, let's keep it at 64K, but I'm going to split when I get down to when I get up to the 64K and just above it, and it's going to merge when I get down to, let's say, 1/8 of a basement node's normal size.
Okay, cool. Yeah, and I just wanted to comment so that we've actually been having a pretty lively discussion in the chat room while you were on this slide, and it started with I just raised the question of you said TokuDB stores MVCC data inline,
Mm-hmm.
and I asked him like, oh yeah, oh right, yeah. So where does InnoDB store this? And so we started really getting into that around, so there's the undo table space in InnoDB, and let me try to catch up here. If people want to chime in, feel free.
Yeah, and there's definitely pros and cons to both approaches, right? Like TokuDB, a challenge with storing MVCC data inline is garbage collection. At some point, we want to get rid of old copies of data, and if you have really long-running transactions, we got to hold on to it because that transaction might actually come back and want to take a peek at the row data in its old form. But yeah, I'm always curious about how InnoDB does things like that, but I always am careful about not trying to claim, I am not an expert on the InnoDB side.
I can try and make a comment if it keeps it interactive. So you said that it's hard for you to have long-running transactions in your design. I think it's hard for InnoDB as well, having dedicated undo space. Undo works really nicely when the amount of modifications that you're keeping MVCC data around for, they fit in the buffer pool. And so then it's kind of like a logical redirection to undo to be cleaned up before there has to be that physical redirection. So short to medium length transactions, I think, work probably better in InnoDB. And the longer transactions, I think, would be more of a pain point for InnoDB than they would be for Docutech, if I understand the algorithms right.
I think that's fair, and there is some analysis of that going on. There hopefully, I think I'm part of a webinar later this month where we're going to talk a little about that kind of workload and why this implementation of MVCC might be superior for the use case you just mentioned, Morgan. The other thing that's interesting that we've thought about and we've never done it yet is if we relaxed garbage collection and we put a cap on it, we said, don't ever collect any garbage that's not at least 30 days old. We could add a feature to TokuDB to do point-in-time queries, because that because that data is always there, we could always, kind of backpoint
Right.
the transaction ID and run a query as of 2 weeks ago and get information. The downside to that would be, man, we could really accumulate a lot of garbage over that period of time, and then the cache table becomes less effective because I'm dragging around a lot of old data.
Yeah, that actually sounds similar to HBase has a similar construct where you define a TTL for an individual cell on a record, and records get garbage collected once that TTL has been hit. And so, yeah, you can set it to something. It's in seconds, so you set it, like, for one of our clusters, we have it set to 45 days because, we only need to keep so much data for each record in our system. But that would definitely have some very interesting implications, but it would also mean you'd have pretty big ballooning of your data set at times, depending on what you're storing.
Yep.
I think the isolation level comes into play too. So like for repeatable read, InnoDB has to keep old read views around for a long time. You might have a transaction that was accidentally left open for 8 hours or something. It was holding on to old row versions.
Accidentally.
Yeah. One thing I was going to ask, I don't know if you cover it later on, Tim, or not. I'm still not entirely clear on the relationship between the node size, which I guess I typically would call the page size, but that maybe there's a difference between what you call a node in memory, which is by default 4 meg. I think the block size that you usually write out is like something smaller, 64K or something.
Yep.
Not sure what the relationship is exactly between.
Yeah. I'd actually get into that on the next slide. What,
Okay.
what you're referring to there is what's called a basement node. Before we go to that slide, though, there are certainly some Inno experts on the phone, and I'm always curious. So when people ask me, I have the right answer. How does InnoDB manage what part of a row is actually inline in the B tree and what part goes somewhere else? And the part that goes somewhere else, where does it go?
I can explain that, unless Matt can explain it better.
If you want to try, what it is that it's just the page size. So if you have, if the row fits within the page, then it stores it all in line. So like 16K, for example. One of the things that complicates InnoDB too is it also depends on the row format. So, but what I would recommend is the Barracuda, which then supports the dynamic, or the file format is Barracuda, but that supports the dynamic and compressed row formats. So that's what we're actually going to make a default in 5.7. So that's what I'll talk about is when you're using the new file format. It stores. So if everything fits in line, then it'll store it. But if it's not able to fit it in the page, so 16K for example, then it'll start storing individual columns off page. So it'll start with the biggest one, so usually like a blob field, for example, and then it will store it off in a separate whatever the page size is, and then they'll just have a 20-byte pointer to the page, and then it can chain them together if it needs more.
Okay, so it'll do some kind of, if I had a 128K varchar, it's going to chain a series of those. It's not going to put it out in a heap, so it's sequential. It's actually going to be putting it out into additional pages.
Right, yeah.
Okay.
So the terminology, just for inclusion there, is that InnoDB calls them overflow pages.
Okay.
And actually, I think the rule is that everything will be stored in line. With uncompressed pages, 2 rows need to fit within a page. With compressed pages, just 1 row needs to fit before it starts overflowing. So if a row is by default roughly larger than 8K, then it starts doing this overflow thing. And overflow pages are never shared. They're always dedicated to whatever they're overflowing to.
Okay.
Wasn't there another semantic too, that if you have a blob or a text field, it's automatically put off page, like onto a new page with a pointer? It's not even tried to do inline?
Not that I can think of. I think the rule of if it fits within that 8K-ish, it'll always be in line.
Okay.
Yeah, I think probably what you're thinking of is the difference with the old row formats, so compact and redundant, which were the old like pre-Barracuda, so pre-InnoDB plugin, pre-5.5. It would store, no matter what the row format is, if it'll fit in line, it'll put it on. It'll put it all on the same page. But if not, in the older formats, it would store 768, the first 768 bytes in line, and then the rest off page. But with the new row formats, it'll just store a 20-byte pointer and then the whole thing off page.
Okay. All right. So I think the question, I forget who asked it, but so we've on this prior slide, you can see I've got a leaf node, and within it I've got these basement nodes, 1, 2, ... down to n. So basement node, what we do with those is we chop up a leaf node, and there's a really good reason for that. But so in this leaf node itself, we've got these leaf node, the header, this tiny little thing, and they're really, really small. So it's easy for us, just like all the internal nodes in the tree, the root node, the upper levels of the tree, it's easy to keep all those internal nodes in memory generally, as well as these headers. Which means whenever I go to do a point query, I should only have to do one I/O because I can traverse the tree in memory down to the leaf node, and if I've got a lot of data, I probably can't fit it all in my cache. I'm going to do an I/O to get it. But as you can see in bullet 2 here, if you're running a point query TokuDB with this basement node methodology, we can just retrieve a slice of that 4 megabytes. It's 64K by default. So we take that 4 megabytes, tiny little bit goes to the header, and then we chop up the rest to be these basement nodes. And the really important thing about basement nodes is that bullet 3. I mean, if you imagine, when I do these presentations and I talk about Inno versus Toku, and we have 4 megabyte nodes, there's always 1 or 2 very smart SQL people and operational people in the audience. They raise their hand. I say, what's your question? They say, how the heck can you do a point query workload if every single point query needed to pull 4 megabytes of compressed data off disk, uncompress it to give me back, say, a kilobyte or a couple hundred bytes worth of data? And that's exactly why basement nodes were invented. They didn't exist in the initial implementation of TokuDB. When you're doing range scans, you don't even care, so 4 megabytes is fine because you want lots of data to come back with one efficient large I/O operation. But for point query workloads, it was tragic. And you can certainly benchmark this and try it yourself. You can tell TokuDB use a 4 meg node, and you can configure your table to be a 4 megabyte basement node, and you'll see the behavior that used to exist, which was anytime I want to point query something small within that big leaf node itself, I had to pull all the data back, decompress the whole thing, deserialize the whole thing, get 4 megs into the cache, which had to evict 4 megs out of the cache. It really slowed things down. But the benefit we get by these basement nodes is for point queries, we just go pull just the basement node off of disk and decompress it and give it back to the cache table. As the fourth bullet says, if we're doing a big range scan, we want to do some bulk fetching. If we're doing a full table scan, we'll detect that. We're going to pull back nodes, not basement nodes, because in that scenario, we want lots of data back, lots of row data. So it's kind of a best of both worlds here. When we're doing smaller things, we just go at the basement node. When we're doing bigger operations, range scans, full table scans, we'll pull the entire node or several basement nodes within one I/O request.
And is it? Oh, you're going to get into how you write it out next. Okay, so
yeah. As I was putting together this presentation, I realized I think the interesting thing about fractal trees and what we've done here is, unlike Inno has a requirement where the on-disk block size for a table, index, what have you, is fixed. I think that brings with it a lot of complications. I think it was maybe a design that couldn't be avoided. The way we do compression, it only took me 2 slides to write out what's actually going on. It's pretty straightforward. So 2-step process. Step 1 is when we're going to write out a leaf node, and we have to write the whole leaf node out. We don't ever just replace, if one basement got dirtied, we still have to repack and recompress everything to go back to disk. We don't ever try to stick something into the middle of an existing compressed leaf node on disk. So we do a couple things here. The first thing we have to do is, for this leaf node, we have n basement nodes. We're going to compress each of those basement nodes. We can do it in parallel. So we take a peek at the header and we say, okay, this table is we're using zlib compression. So grab each of these n basement nodes, throw them out to one of these compressors, and have each basement node in an in-memory buffer get compressed. So in here, to the left we see the uncompressed basement node 1, basement node 2, basement node n, and you could think of this, pretend it were drawn to scale now. So basement node 1, when it to the right, when it compressed, it's certainly smaller than its existing representation. And 1 through n uncompressed are similar in size, but from a compressed perspective, your data could compress differently based on the rows that fit in those nodes. So basement node 1 is certainly much smaller than basement node 2. Basement node n is smaller than node 1 itself. So each basement node compresses as much as it can. There's no retry. It's compress each basement node and get those things ready to go to disk. So step 1 is take all the basement nodes individually, compress them in memory buffers to their compressed format. Step 2 is this. Well, when we go to put the header on disk, the existing header in memory knows these offsets and the key ranges from an uncompressed perspective. So we have to recalculate these offsets because the data is now compressed. So what used to start at offset, say 64K, the second basement node 1 compressed. So now the offset is, in this example, 16384, for example. So we rewrite the header for these offsets. Header's tiny. It's more drawn to scale at the bottom of this slide. And we pack it all together. So we take the disk-based header. We then lay that next to compressed basement node 1. That goes next to compressed basement node 2, ... out to compressed basement node n. I intentionally drew these, the header and the basement nodes near each other, but not actually physically aligned, the end of one to the beginning of the next, because there does need to be some level of alignment going on for I/O efficiency. If you're going to use direct I/O, you can't just do reads at any point off the disk. The I/O has to be aligned. So I believe we do 512 byte alignment, but there certainly is a little cushion between the header and basement node 1, and then a little bit between basement node 1 2, unless the compression actually ended on that exact alignment. That becomes a single byte stream, and it just gets written to disk as is. So for us, that existing, the 4 megabyte leaf node in memory, it existed at basement nodes. All the basement nodes got compressed and laid end to end. Little header goes in the front of it. When it's time to go to disk, it might be 4 megabytes might have become 384K. It might have become 381K. It doesn't really matter. Our on-disk representation, there is no fixed size. So when TokuDB goes to write to disk, it just writes. And on disk, I believe our block allocator, we do something like a 4 kilobyte alignment. So there might be a little bit of slack in the file system as well, because we can't just begin writing at any point on the disk. We have to actually do some alignment for direct I/O compatibility. Any questions on that?
There is a question in chat. Yes, just for clarity's sake, so TokuDB to InnoDB, is a node in TokuDB roughly equivalent to an extent in InnoDB, and then a basement node is equivalent to a page?
No, a node is equivalent to a page. It's just our page is so large, we subdivide the page into, you could call it a subpage. We called it a basement node. So from an InnoDB, if you looked at it from a tree perspective, it is what I showed right up here. So that leaf node in the lower right-hand corner, you can certainly think of that as a page in InnoDB. Because in InnoDB, a page is the equivalent to a node in the B tree that makes up InnoDB.
Tim, another question for clarification while you're on this slide. It sounds like 4 megabytes is your uncompressed size, whereas the comparison to InnoDB, if you were talking compression, that's the compressed size as well. Is that fair or true? I.e. the 4 megabyte pages, once divided up into basement nodes and written, that's not going to be 4 megabytes of I/O.
Correct. Yeah. I mean, rule of thumb, I tend to see people getting about 5-to-1 compression, give or take. So normally a 4 megabyte block on average data, a 4 megabyte node becomes somewhere around 800 kilobytes. Okay.
And your basement nodes being default to 64 kilobytes, that spans from that experiment that you've done that says about 40, 50 kilobytes is what you need to have to get compressible data. So if InnoDB were, and you have to make the basement modes individually compressible, so that you can jump to them at random. Is that?
Yeah. So this, let's call it compression wars, right? The compression wars are going to get interesting. It looks like it's a 5.7. I don't know if it's a lab or something that will be part of 5.7. On the InnoDB blog, they talked about supporting 32 and 64K pages. But specifically in that blog, it said, but they won't support compression at those sizes yet.
Right.
I assume at some point they will, and when they do, compression gets more. The battle gets a little more interesting because now we're starting with the same amount of data, right? It's an unfair battle at the moment because I'm compressing things in 64K chunks, InnoDB is compressing in 16K chunks, and independent of this target blocks, the key block size problem, I'm looking at 4 times more data when I do compression. And when you zip things, bigger things tend to get smaller because the compressor gets to see more repetition and therefore make things smaller.
Right. That's interesting. Thank you for detailing that.
So is it? I'm trying to think about it in my head. I wonder how wrong I am. So you have this. So you have. Well, if I can get back. Okay, to your slide. So you have this leaf node, which is the 4 meg by default. So, and that's uncompressed. So then when you go to compress it, you break it up into these 64K chunks by default. But
Yes.
that's after the compression?
No, we compress. What we do is right here. So on the left side of the screen, let's call that an in-memory leaf node, right? It's got a header, which is really, in reality, tiny, but I had to make it big because it contains a lot of interesting stuff. And below that, you have these basement nodes, 1, 2, ... n. Each of those basement nodes is about 64 kilobytes by default. When we go to compress things up, we're compressing these basement nodes individually. So we're not taking the whole 4 megabytes and compressing it all at once. We're doing it in 64K chunks. And the reason is, if we did it all in one 4 megabyte swoop, then for a point query, I'd have to peel that entire compressed 4 meg blob off of disk, decompress it, deserialize it, and get it into the cache. So to make sure that our for full table scans, that's a win. You'd want to do that. But if you're doing any kind of OLTP, you need smaller digestible chunks. Otherwise, performance-wise, it's just going to completely tank trying to keep up with the workload. You're just going to spend far too much time decompressing and peeling too much off of disk. Then you will be able to keep up. So from a compression perspective, if we were to compare and contrast this versus Inno, just at a very high level, to talk about like the compression characteristics or the performance characteristics, doing it this way at the moment is a win for TokuDB because even though we're not compressing the whole 4 megabytes at once, we are compressing it 64K at a time. So we're looking at about 4 times the data for each compressible unit compared to an InnoDB 16K page. So first off, we've got an advantage in that respect. The other advantage we have is we just take these chunks, we chop them all up, and as this slide shows, we just lay them end to end and they go out to disk. Where currently with InnoDB, you pick your key block size, your on-disk size for that table. You compress the 16K. If it's not smaller than the key block size, InnoDB goes back to the drawing board, says, okay, we got to split this node, and then we got to recompress these 2 now split nodes, which is a lot of time and a lot of CPU for compression misses. When InnoDB compression hits, I think it does a fairly good job at performing and keeping up. But when these compressions have a miss, then it's a split and a recompress that has to occur.
Yeah, and that's where with the modification log tries to minimize it to some degree, but it certainly doesn't entirely, or anything close to entirely. But so I'm curious. So we have this 4 meg, page, or what you call node, and then we compress each of these 64K blocks. So then we end up with something like that's 1 meg in size, let's say. Do you then do some additional kind of LSM tree style write aggregation before you do the write, or then do you just write out this kind of random sized?
No, we just write out that you hit the nail on the head. That random sized, each fractal tree. Another difference between TokuDB and InnoDB. InnoDB has, I think you can use table spaces or you can use file per table for your on-disk representation. Fractal trees in TokuDB at the moment, it's file per index, so it's actually a level deeper than InnoDB. Each index, each tree has its own file, and within that file we do copy on write, basically. So when it's time to write this leaf node out to disk, we look at that file, we ask the block allocator, we say, hey, we need a contiguous, in your example, 1 megabyte chunk in this file. The block allocator uses a first fit algorithm. It says, oh, there's a 1 meg chunk available at offset 32 gigabytes, a certain bytes into the file, and then it just writes it right down into the file that way. But on disk, there is no fixed block size in TokuDB the way there is in InnoDB.
Okay.
It's completely variable. And again, trade-offs, right? With the nice thing about fixed on-disk block size is you end up, fragmentation-wise, it's a different problem because the holes can always be refilled because everything going to that disk is the same size in InnoDB. Whereas in TokuDB, we can be more compact. We're not beholden to this fixed size, but the challenge then becomes how do you not end up with holes in the file that can't be reused?
Okay, makes sense.
Lots of interesting trade-offs. What I promised to talk about a little bit, I've got just 2 more slides, Jeff. I've learned a lot of lessons here from a compression perspective. These are kind of my top 2. Slide 1's about rotating disks, and the second slide's about flash. So it really is as black and white as it says right here. So on a rotating disk, higher compression is usually a win. So any table in TokuDB, you tell it use LZMA for extreme compression, use QuickLZ for light compression. We're adding Snappy. I find on rotating disks either zlib, which is the default kind of middle of the road, or LZMA is a win. And the reason for that is the cost of an I/O on a spinning disk is normally measured in milliseconds, as long as your data is much larger than cache. The cost of decompression is measured in microseconds, so orders of magnitude of difference there. So spending more time decompressing is not a big deal if you can save an I/O. So at the bottom here, spinning disks, using LZMA or zlib compression, using these bigger basement node sizes, 64K and 128K, it's generally a win. Because if I can save on Sysbench, for example, I can conserve I/O. I can do 1 less I/O for a range scan, for example, by using LZMA compression, and I win there. The flip of that is SSDs and flash. Well, cost of an I/O on flash is generally measured in microseconds. It might be less than or equal to, or similar to the time, the cost required for decompression. So in that model, you want to use something like a light compression algorithm, QuickLZ or Snappy. You might want to really draw back your basement node size to something like 16 kilobytes. It definitely depends on the workload, but the reason here is if you don't do these things and you run a benchmark, you want to see how fast I can do point queries on a much larger than cache workload on flash. What you'll see is TokuDB will do, say, 1,000 queries per second in its default configuration. Then if you make the compression lighter, you make the basement node smaller, you'll start driving way more I/O through that system because the system's not sitting there idly using CPU to decompress. It's ready to do the next I/O. So it's an interesting challenge. A lesson learned here is there is tuning to be done. What works on spinning disks for TokuDB does not necessarily work on flash devices. From a configuration perspective, you might have to be playing with compression algorithms and or basement node sizes to get the best performance.
That's actually, I really like this slide, Tim. This is really good information because that was one of the challenges that I was actually curious about was with solid state, you're bound by actual raw amount of space you have, not the I/O. And then in our case, at least, CPU is actually kind of a tight resource for my team. Because of a lot of sorts and stuff that we have going on in our server. And so, Snappy I've found in general, like we have some applications that write records that have been Snappy compressed instead of using it inside of the server. It'll make a decision, is it worth compressing this better or not? And sometimes some Snappy compressed data will basically just be the data without maybe a byte or two in the beginning or end. And then other ones will be, a full-on compression. So.
Yeah, I mean, one more short story I can share. We're adding Snappy compression to TokuDB. It was contributed by someone who works at Taobao in China, And I'm a benchmarker at heart. I don't like to put a feature in TokuDB or TokuMX without really testing it and making sure we're getting what we think we're getting. So I was testing on my desktop with a nice, a high-end consumer-grade SSD, and I was testing Snappy against QuickLZ. And my theory going into this was, if I just do point queries and I have to go to that SSD, if Snappy can decompress faster, then Snappy should run more point queries per second. But QuickLZ was beating it, and it took me a while to get to the bottom of the problem. The problem was that I was actually bandwidth limited on my SSD. I was hitting 520 megabytes per second of throughput, but because QuickLZ was doing better compression, I was getting better throughput. So I was doing more IOs per second with QuickLZ, which I could do because I got more compression. I needed less bandwidth on the SATA channel. So it's kind of weird sometimes when you really start playing with compression and node sizes, and you can probably see the same stuff. If InnoDB at some point adds additional compression algorithms, you find other bottlenecks in your system that you didn't realize could happen. I've never tapped an SSD before from a throughput perspective. I've always tapped out my I/O systems on IOPS, for example. I never thought to look at how many megabytes per second were going through a device until I did Snappy benchmarking. So it's a brave new world with some of these compression algorithms and some of these I/O systems that are just so fast. Kind of the other thing we were going to talk about today, that I/O capacity, it's probably a similar problem. Some of the baked-in stuff to InnoDB was probably like TokuDB. When it was created in a world of spinning disks. And then you start having Flash and turning knobs to try to understand where things are going.
Tim,
Yep.
question. Read-only in memory. Do you have like a decompression buffer in memory or anything like that?
Say that one more time.
Read-only in memory. Because if you're doing decompression, even if it's about the cost of an I/O, in the case where you didn't have to do an I/O, do you have a buffer to be able to read decompressed?
No, so from an in-memory perspective, we've got our cache table just like the InnoDB cache table, and for the most part, there's some stuff that historically has existed. There's the ability in our cache table at some point to keep some of the data, internal and leaf node data, around, but compress it before we evict it from the cache table. But over time, I think we're finding that's not a good idea for the use cases we're seeing. So certain people, like if you get really high compression, another pro tip on TokuDB, if you use buffered I/O, for example, and you give half your RAM to the cache, to the TokuDB cache, the other half of your I/O, your OS buffers are going to hold compressed versions of your TokuDB data, so you can get really nice throughput on read-heavy workloads on high compressed data, because rather than going to disk or flash or something else, we're going to do those reads out of the operating system buffers. So we've had some users who have like 32 times compression, and there's no way they can have a big enough cache table to hold all their data, but they can certainly afford enough RAM to keep that much compressed data in the OS buffers.
Maybe I'll paraphrase. The pages as they're stored in memory, are they decompressed or compressed?
They're always uncompressed.
Always uncompressed, okay. So if you did have a read-heavy in-memory workload, you wouldn't have a lot of decompression to re-decompress rows to read them. Nope,
you'd have none at all.
Okay.
I mean, and we're, I'll put the Toku Tech hat on right now. We're constantly chasing you guys and Dimitri and his, 1 million QPS, 2 million QPS numbers. InnoDB it's phenomenal at in-memory point queries. With clustered secondary indexes, I think we can keep up on in-memory secondary range queries, or probably win. But everything else in-memory is just fabulous with InnoDB.
Just out of curiosity, I think it's related to Morgan's question. So, if I doing a point query, for example, and we can read in just that 64K.
Mm-hmm.
We uncompress it, and then I update that same row. Is it immediately compressed and written out, or there's like an LRU that just evicts it at some point later, and then it's compressed and written? And I'm also curious, so do you store offsets for the basement node, so then you just write that individual basement node, or do you have to read in that full leaf node and then write that
Okay.
back?
Yeah. What you're describing there really gets more into fractal tree specifics than how we
I was
handle
just
compression.
curious. If it
No,
takes a
no,
long
that's fine.
time to
But to
explain.
that example, what ends up happening is my screen share on again.
Yeah, you're good.
And can you see my mouse pointer?
Yeah.
Okay. I mean, the whole point of a fractal tree, big nodes down on the leaf nodes, that's storing row data. The great thing we do about big nodes and these internal nodes is message buffers. So almost every operation we can buffer in these upper nodes. Let's pretend we dropped it all in the root node. We don't really do that, but we could. We did at one point. So if every single churn, an update, an insert, a delete, if it just hit a message up here, then between checkpoints, I'd be dirtying up this node in memory. And then when I hit a checkpoint, which for us by default is every 60 seconds, I can do an awful lot of change in 4 megabytes. And if it didn't all get held here, if it spilled over in the fractal tree to these 3 nodes, for example, when I hit the checkpoint, I only have to compress and write out these 4 nodes right here. It takes a while, and it's rare for the messages to come from here to overflow to this leaf node, internal node, to overflow to the leaf node, to dirty the leaf node, to then have to write out the leaf node itself. So that's part of the fractal treeisms here, that we're buffering a lot of the change up here. And I think I did a presentation on this in the past here, but you can find my stuff online.
Yeah, I'm remembering it now. Yeah.
It's similar. I mean, InnoDB has a big fat secondary index change buffer where they can buffer inserts, updates, and deletes. And it's kind of an interesting beast. I constantly try to get more information about it, and I think some point we can probably get some InnoDB people on here to go deeper into the algorithms and like why doesn't it just buffer forever, or why does it, when it does it have to spill over? So really the InnoDB change buffer's over here just for secondary indexes, and it's big. For us, we've got lots of directed change buffers and at all internal levels of the tree. And we're buffering a lot of the modifications, the mutations, so that at checkpoint, if I did an insert that hit that leaf node and this leaf, let's say we had 1,000 of these, I definitely, at my next checkpoint, I don't want to have to write out 1,000 times 4 megabyte nodes. If I can catch all that in, say, the top node or these 4, then I'm doing a lot less churn and writes between checkpoints than I otherwise would have to. Because that would kill us. If every single insert actually went down the tree into these leaf nodes, I'd be doing nothing but checkpointing. Once I finished the checkpoint, I would have to start my next one because a minute has probably gone by.
Okay, yeah, I do remember you going over that. I think that might have been the last time I was on DB Hangouts, actually. But one thing, and just real quickly, if you were curious about the change buffer, if I remember correctly, there's a hard-coded limit to it'll only grow up to 10%, I think, of the buffer pool size, and so that's when, and then it'll start having to flush all the changes out to secondary indexes.
It used to be up to half in 5.0, 5.1, the full plugin. I think it was reduced down.
Yeah, I think it's 10%. That's just off the top of my head. That's what.
It needs to be instrumented.
Yeah, I mean, but a lot of things we'd like to revisit. That's one of them.
But the change buffer is an interesting little beast because as a benchmarker, you turn the change buffer off on an insertion workload. Holy cow, does it make a huge difference? But even at that, if you grow your data big enough, eventually it still becomes the same asymptote. Like if your data gets large enough, at some point that change buffer can't buffer enough to really start paying that I/O penalty on your inserts. But it really stretches out for a very long time before you hit that point. But turning it off is eye-opening. I'm not an operations guy, but I'd assume I don't know why anyone would not turn that thing on and leave it on, because with it off, it's kind of painful for really high throughput applications. But Jeff probably has an example of why he turns it off.
Well, if you have secondary indexes, yeah, it's huge. And I guess if you want, I can. I pasted a link in there that talks about. Oh, and Daniel pasted a link about InnoDB change buffer max size too. But I posted a link in the chat that kind of goes over just the kind of the high level details. Also, it defaults to 25%, but it's not hard coded. So it shows you what I know. Yeah, so you can go up to 50% for the change buffer max size. I posted a link in there that just talks about the current compression.
Yeah, it's this link I have up here, I think, right? The compression works for InnoDB tables.
Yep. Well, the InnoDB compression internals, yeah. Is that the same one?
Yep, one sec. There we go.
Yeah. So we only got 10 minutes or so left. So if you want to kind of learn a bit about how it works now, you can read that. It's not terribly long, and I think it's pretty well written. That's the way that it is today, and the way that it's been since it was introduced. The InnoDB plugin, which was, if you remember, in MySQL 5.1, there was the built-in version of InnoDB, and then you could also use this InnoDB plugin. So it was a way to kind of provide some new features in MySQL 5.1. Again, that was one of the first things that happened after Oracle acquired InnoBase. But one of the new features was compression. And so it really hasn't changed since it was added. And that was the spring of 2008. I think April was the first release. So with the time we have, I won't spend too much time on where we're at now. You can see that there on that page. But that adds a lot of complexity to InnoDB. So basically, of course it has to manage itself, the compression and decompression, and as you read through that page, there are some additional kind of unique behaviors that result. Storing the compressed page inside of the log. It has this modification log that it uses to try to avoid page splits and unnecessary recompress cycles. So it just adds a lot of complexity, and what we're hoping to do, what we hope to be the future, is to rely on transparent page compression. You may have seen that labs release that we put out that included it, and it's a little bit different from the MariaDB and Percona both have something similar. The difference between ours and theirs is just that ours is a bit more, at least I haven't looked at theirs in a while, so I'm just talking about the original. But focusing on ours, it's not specific to any NVMFS implementation. So this whole kind of thing started off with Fusion.io and their DirectFS, which is their kind of closed source commercial NVMFS implementation. So it supports transparent page compression. But ours can be used with any file system, well, any operating system file system combination that supports sparse files and punch hole. So what happens is, with our transparent page compression, and just so you know, it's supported with, if you're using a recent Windows version, Windows supports punch hole with NTFS, Solaris 10 and 11 do with ZFS, FreeBSD does with ZFS as well, Linux does with recent versions of ext4 and XFS. ButterFS also does. So just so you know, it's not uncommon at all today, and we're hoping that in the not too distant future, basically we can assume that any of our users will have that support on the file system side. The one notable exception today is HFS Plus. So if you're using OS X, you don't have support for sparse files generally. But you can specify zlib as the compression algorithm, or you can use LZ4. So those are the two that we support with the transparent page compression. And with the transparent page compression, it just eliminates all of that complexity. So basically, you don't have to specify. Well, you don't have to specify it anyways, but you don't have the notion of a key block size in addition to the page size. So that's not something that you ever have to worry about or think about. The key block size being essentially the compressed page size. You just say, I want to create this table, and you say compress equals zlib or LZ4. The default being zlib. And then InnoDB doesn't have to worry about it either. It all happens underneath. So when it does a write, so write the page size, whether it's 16K or whatever the page size is, 4K, 8K, 32K. And then the underneath, basically InnoDB just says, okay, I'm going to write out this page, and when it opens the file, it makes some additional F controls or file flags to say that we want punch holes. We need punch hole support, and basically then it calls punch holes. So we could be writing out this 16K page, but we've only got 2K of it that's actual data. So it'll punch a hole in that and remove everything, everything at the end. So we're not writing out all of this extra data that we don't actually need, or that doesn't actually have data. All the zeros that don't really do us any good. And the upside there again is it removes all that complexity from the InnoDB side. It's all transparent, and you actually get better performance. Now, if you read through that page, you'll see InnoDB has to do a lot of work. And in various ways it tries to limit the performance overhead of the compression, but it's still noticeable. I mean, if you're doing sysbench stuff or if you use linkbench, whatever you're using to measure the performance, you're definitely going to see a hit. But in our tests, we actually saw slightly better performance when using the transparent page compression. The reason being that you're doing less actual I/O. You're reading and writing less to the actual storage device or the block device. So that's what we'd like to be the future. It's starting. Well, we hope to get that into the 5.7 GA. As I noted, there's a labs release out there already. But at least for 5.7, you're going to have the option of either one. So the old style compression or the transparent page compression. We hope that the transparent page compression will become the only thing that's needed, but that's still unknown. But that's definitely going to be the preferable way if it's an option for you. And generally it is. Like I said, that there's some exceptions. For example, HFS Plus, on OS X doesn't have the underlying support that we need on the file system side.
Hey, Matt.
Uh-huh.
What I can say is we did some experimental work internally. Since we don't have a fixed block size in our files on the file system, we implemented hole punching to eliminate fragmentation and make our files smaller on disk. We're happy Oracle is, MySQL is pushing this forward. We do have I don't want to be a FUD-monger because I don't have data, but one reason we backed off is a concern. Someone's got to go first and do this. The doing a lot of tiny hole punches in a file system over time, I think that's my concern right now, is just seeing what the long-term potential impact is to performance. But it would be great if anyone from MySQL or the Inno team can share some of their experiences. They've done a lot of it. That was our one concern. It does freak people out when you do an LS and you see a file that's way bigger than it really is. But that's an education problem. That has nothing to do with performance and correctness. But my fear was, especially like at the you're going to be punching a lot of tiny holes. And if you go, we did it with XFS originally, and talking to the people, the XFS maintainers, there was still kind of this, and this was a year and a half ago, so things are probably better now. But at some point, I would love to see some long-term. Someone at MySQL probably has internal apps stood up doing this continuously, and understanding, are there any downsides to hole punching?
Well, I think the general downside is that it's just it's relatively new. The support is relatively new for it, and XFS, being an example, ext4, ZFS has been around a bit longer, but ButterFS is just brand new. Mm-hmm. So I think that's just the bigger concern, is that in some cases we don't have that support, so it's not even an option. In other cases we do, but it's new. It hasn't really been tested thoroughly out in the wild to a large degree. So even for Fusion.io's DirectFS, we've ran into some problems in our testing. So this is why
we want you to get it into 5.7. Then you can go first.
I might try and speak to his answer as well. Tim, I did have a chat with Sunny about that.
Yeah.
And he's been doing some experiments to burn in an installation over many months to see how performance degrades, because it's a new type of fragmentation. One of the interesting good things for us about this being simpler is we're passing down a layer of complexity to a layer below. and they have to manage that. Obviously, there's no such thing as a pre-launch, and we'll probably find bugs within that, and we'll have to work with those teams. It'll also be interesting that the fragmentation may differ by operating system, based on that we're relying on those implementations at the layer below. Mm-hmm. So that will be a subset of problems on its own, that we support many operating systems, and some will have better support than others. So
yeah, I'm actually
interested. You take a step forward, you take a step back as well.
I'm interested if, like John, Jeremy, Daniel, have you guys had to deal with punch hole or sparse files at all in file systems? Seen a lot of shaking heads, right? Yeah, I haven't personally, and I don't understand the ramifications of it as an operator.
It's creepy, but it's really cool. I mean, it's awesome when you do it an LS with the right parameters, and you're like, oh, my file's only 10K, but then you do it wrong, and it's like, oh my God, my file's 2 terabytes. Like that shouldn't happen with InnoDB, but every single Linux command has like 2 ways to run it, and some Linux commands aren't even aware of sparse file systems, and those are the ones where you could over-provision your file system if you're not careful. But again, I mean, to my point, I'm happy that MySQL's pushing this forward, because Inno will definitely be punching way more holes than we do. So once it's up and running for Inno, we're happy to enable it in ours as well. And then that eliminates the internal file fragmentation dilemma. Like anything within the file, we could just trim it out. We don't have to actually move, kind of defrag our files at that point.
Right. Okay. Well, we completely blew out our time on all this stuff. So I've got plenty of stuff we can talk about next time. Any last thoughts or questions before we wrap up today?
I was just going to say real quickly that we're aware of how good TokuDB is, in compression and on those specific workloads. We're amazed, and there's a related work that we would like to do in the future that. Related to compression, for example, supporting heap-oriented or heap-structured tables, and then we don't have to worry about the change buffer so much, because secondary indexes aren't going to be so painful, but a whole range of things. I just wanted to note that We see a lot of the advantages, like as Tim said, there's trade-offs to everything, but we see advantages to various things and methods that TokuDB uses, and we want to add various features that aren't necessarily directly related to compression, but will make a big difference in certain cases.
And I have a quick plug, if I may. Matt and I are working on new defaults for MySQL 5.7, and we want input. So if anyone is listening and they have suggestions, I had a recent blog post from Planet MySQL. We would really like to know what ideas you have.
Where is that? Where can people respond to that?
You can email me. You can write a comment on the blog. You can write your own blog post. Any way to get attention.
And your blog on Planet MySQL?
That's right. It'll be pretty close to the top, saying what changes would you like to see in 5.7.
So is that talker.ca?
That's the one. Yeah.
Right, so that's just www.talker.ca.
Yeah, and I'll have a link in the show notes for it too. But yeah, make sure you check it out. And it sounds like this, sometime next week. So get in there and get your opinions in quick, I guess.
Yeah, and bigger page sizes and LSM trees with Bloom filters. I was going to throw that out there too. If people are watching, they might be wondering if we've considered and if we're thinking about that kind of stuff. And those are also related things that we've talked about for future releases.
Okay. All right, well, I guess we're all wrapped up, so we'll see everyone in 2 weeks, and hopefully by that time we'll have the Percona schedule and the speaker list will be released, I'm hoping, fingers crossed, see who all is going to be there and talking. Yeah, we can move on talking to the other stuff we didn't get to today, so the event scheduler, InnoDB I/O capacity, talking about that a little more. And actually, might even see if we can get Marco, since you guys had mentioned, did a lot of work on InnoDB compression, to talk about that a little more in depth.
Yeah, I'd be happy to ask him. I don't know if we'll have success in him recruiting him, but
Well, yeah, if you can, that'd be really helpful instead of me cold emailing him for it. So.
Yeah, I can definitely ask him. No problem.
Cool. Okay. All right. Well, thanks very much for attending today, all, and we'll see you guys next time.
All right. Thanks, guys.
Thank
Have
you.
a good one.
Thanks.